Washington Seattle Engage program. And this year we also are lucky enough to partner up with Davis Technical Books. So together we all host a series called UW Science Now as part of the Seattle Science Lectures, which is sponsored generously by Microsoft, Boeing, and the Bill and Melinda Gates Foundation. So tonight, each speaker's program will be about 25 minutes, and that includes 5 minutes for any of your questions. And then there'll be a 5-minute intermission between speakers. In that time, it's a good idea to use a restroom. There's some gender-neutral restrooms next to me, or grab a drink at the bar. So before I introduce our first speaker, though, I want to give you all a plug for our next event in the Science Series. And the next night of the UW Science Now Speaker Series will be held right here at the Technical Books on May 10th at 7:30. At that talk, Katie Rickard will speak about opioids. Sam Entwistle will talk about cell signaling and diabetes. And Emilio Villanova will tell us all about the dynamics of tropical rainforests in the Amazon. We all good. No worries. All right, and now for our first speaker. So, shots aren't fun. And they're especially not fun when they deliver a vaccine that's not effective enough. But what if there was a way to both eliminate shots and make vaccines more effective? Our first speaker tonight will discuss the design of a new vaccine method and the challenges needed to addressed to make it a reality. So please give a warm welcome to the woman who ain't in with injections, who knows all about the boo in boosters, and who is personally helping to take a bite out of HIV, Miss Rachel Creighton.
Thanks, Warren. Those jokes were awesome. Hi, everyone. I'm Rachel, and I'm a bioengineer. That can mean a lot of things, and in the next 20 to 25 minutes, you'll find out exactly what I do as a bioengineer. So I'm a scientist, and as a scientist, I really like to talk about science. But I also really like art. So we're going to start this talk by looking at a little bit of art. This is a painting by Norman Rockwell. It's called Before the Shot. It appeared on the cover of a magazine called the Saturday Evening Post in 1958. And the 50s were a really interesting time for vaccines in America. A few years earlier, a polio vaccine had been licensed, and at this point, we were in the midst of huge mass vaccination campaigns. And much like there's a lot of controversy around vaccination today, there was a lot of controversy back then. A lot of distrust of doctors and skepticism about what was in these vaccines that everybody was being told to get. So maybe Rockwell's intention with creating this painting with a little bit of humor was his attempt at easing people's anxieties about getting these shots. So let's look a little closer at this painting. Now the first thing that probably draws your eye in this picture is the butt. And based on the title of my talk, you might be thinking that I'm going to spend the next 20 minutes talking about butt cheeks. I'm really sorry to disappoint. That's not what we're going to talk about. I'm actually referring to the cheeks on your face, specifically the inside of your cheek and your mouth. So I'm working to create a future where, instead of holding a needle, the doctor in this image might be holding something that looks more like a Listerine strip. So the vision is that we would load our vaccine into a system that looks like this. You would press it into your cheek, it would dissolve in a few seconds, and then you'd be on your way. So before we talk about how that system will work, let's look closer at all of the problems with our current mode of vaccine delivery, these shots with needles. So the first problem is that they hurt and they're scary. And because they're scary and they cause so much anxiety in so many people, a lot of people avoid seeing their doctor and avoid getting these shots. A second problem is that they require trained medical personnel to deliver. It takes a doctor or a nurse who's trained in delivering vaccines to give these shots. And so this is a really big problem in places where doctors are rare and infectious diseases are really prevalent. The people who need these vaccines the most, it's really hard to deliver them. And then the third big problem here is the needle itself. So these needles need to be disposed of safely, and in places where that's difficult to do, such as rural areas or the developing world, these needles can accidentally stick people or they may be reused, and these things will spread disease instead of preventing it, which is what we want. So despite all these problems with shots and needles, the history of vaccines is really one of success. So I have a few illustrations here of terrible diseases like smallpox and tetanus and polio, and thankfully these images are really things of the past, thanks to massive public health efforts, including things like improved sanitation and public education, but also vaccines are a really important component of that public health effort. Unfortunately, there are many diseases today for which vaccines are not a part of that effort, and having a vaccine for some of these infectious diseases could go a long way towards controlling them. Part of the problem, though, is that our current vaccine design and delivery strategies are not effective for a lot of these infections. So if we think about this problem in really simplified terms, we have two options. We can either redesign the vaccine itself that we're delivering, or we can redesign the delivery system. So this takes us back to this vision of a vaccine in a Listerine strip. So I've outlined how this system would be really great at eliminating all these problems with shots, but how will it change the efficacy of the vaccine? We actually think that it can make some vaccines more effective. So the reason we think that is because vaccination is really dependent on the site of delivery. And a lot of the infections we'd like to prevent occur at places like your nose, your mouth, your lungs, or your gut. And we call these mucosal surfaces, so you're going to hear this word a lot in the next few minutes. So scientists who study the immune system have discovered that if we can deliver vaccines at these mucosal surfaces, we can potentially make the vaccines a lot more effective. So to illustrate that, let me tell you a tale of two vaccines. Once upon a time, there were two brothers. The first brother, Jake, received a flu vaccine delivered in a needle. The second brother, Elwood, received a flu vaccine delivered in a Listerine strip type of system in his mouth. In both brothers, these vaccines consisted of a little piece of the flu virus, and because it was just a piece of the virus, it didn't make either brother sick. But specialized immune cells in their bodies recognize this little piece of the flu virus as something that they should prevent from infecting the body. And so part of that defense strategy is the production of molecules called antibodies. So the function of these antibodies is that if these brothers were to get exposed to the actual flu virus, the antibodies would be able to recognize the virus as something that needed to be eliminated and could either neutralize it right away or mark it to be eliminated by other cells in the body. So right now this is a pretty boring story. It looks like the brothers are going to have the same fate. But if we zoom in on a mucosal surface, we'll zoom in on the cheek, we'll see that maybe they'll have a little bit different fates. So to orient you here, this is a cross-section of the cheek tissue. So we have a layer of saliva which contains a lot of mucus layering the tissue. Right under that we have the very surface layer of the tissue called the epithelium. And under that are more layers of tissue, and the important thing about these tissues is that these contain these special immune cells that can recognize these germs and react to them. They're called dendritic cells. So if you look at the cheek tissue of both brothers here, we'll see that in Jake's cheek we see some of those antibodies in his tissue, but in Elwood's cheek we see the same antibodies in his tissue, and we also see these other kinds of antibodies that are in that saliva and mucus layer. So the brothers commute via bus, and if you commute via bus, you probably know that there are a lot of germs that you're exposed to. And so inevitably on their bus commute, those brothers are exposed to the flu virus. When Jake's exposed to the virus, it moves into his tissue quickly, and his systemic antibodies do the best they can to eliminate it, but they just can't fight off all of the virus, and so he becomes infected. But in Elwood, when he is exposed to the virus, these antibodies in his saliva can work to attack the virus, and then the virus that does enter his tissue can be neutralized by the antibodies that are in the tissue. And so Elwood remains healthy, and he takes care of his sick brother, and he tells him that next time he gets a vaccine, he should make sure it's delivered at the site of infection. The end. So hopefully you can see from that story that by delivering vaccines at the site of infection, we can help our bodies build up this second, more local line of defense, which can lessen our chances of getting sick. So this is great in principle, but it's really hard to deliver vaccines at all of these different mucosal sites where all of these different germs enter our bodies. And while a system that looks like a Listerine strip might work really well in the mouth, you can imagine that it'd be pretty hard to translate this same system to places like your nose or your lungs or your gut. So this isn't great because what we really like is a system that's very generalizable, so we can do all this development work, have a system that will work for any vaccine. The good news about this is that if we look at some of the different mucosal sites in our body, like the nose, the mouth, or the gut, we'll see that these cross-sections look a little bit different. There's a little bit different structure of the tissue. Maybe the mucosal layers a little bit thicker, thinner in different locations, but they look pretty similar. And there's actually evidence that all of these sites, the cells and immune mechanisms that are present, all can communicate and work together as part of a more common mucosal immune system. So what this means is that we can, in theory, design a single delivery system to work in the cheek, and we could get protection at all of the other mucosal sites in the body. Okay, so this is awesome. We can eliminate shots. It's generalizable to a lot of different germs, but delivering things into the cheek is actually really, really hard. So there's a couple physical barriers and barriers within our immune system that make this really difficult. So you're probably familiar that the saliva that's in your mouth helps get the food that you eat wet and helps you swallow it. Well, it also acts as one of our body's first lines of defense against invading germs. And so the flow of the saliva helps to wash all of this junk out of your mouth. We also have a lot of enzymes and proteins in our saliva that help to break down food and break down these germs that are trying to invade. So you can imagine when you're thinking about these things that if we just deliver our vaccine in bulk to our cheek, these same enzymes are going to attack our vaccine, and the flow of the saliva is going to wash it away. And so what's going to happen is our vaccine isn't going to be able to get to those special immune cells that need to see it and react to it. So what we really need to do is just part the Red Sea of the saliva, and ideally what we'd really like to have is just create a path directly to those immune cells and deliver our vaccine right to those cells specifically. And there's actually a way to do this using microneedles. So the vision with this system is that it would be fully dissolvable. We'd load our vaccine, you'd press it in your cheek, it'd deliver it directly to these cells, and our vaccine would work great. So I'm really excited about these microneedles, but I've been told by some of my classmates that they look a little scary, and so you might be thinking something like this right now. based on this image. So I have two fun facts that might help ease your fears. So the first is that these microneedles are actually painless. And the reason they're painless is because the way we feel pain is through cells that live fairly deep in our skin and can sense changes in pressure and things like that. And so these needles are actually short enough that they don't reach those cells, and so you don't feel any pain. Now, maybe that's not a very convincing argument if you don't know what those cells are. So here's another fun fact that might help. So this is a hypodermic needle drawn to scale based on the actual needles that are used to deliver flu vaccines. And here is the actual size of the microneedle arrays that I'm designing compared to that needle. So you can see it's a lot smaller, and to help put all of this into perspective, this is a photo of the side of a quarter that I took. And so, yeah, this is all to scale, so you can see that the needles aren't even as tall as the thickness of that quarter. So they're really, really tiny. The texture is sort of like Velcro or like really coarse sandpaper or something. So hopefully that image doesn't look so scary anymore. And yeah, again, the vision is just that we'll have this system, it'll completely dissolve and deliver our vaccine directly to these cells. And so that seems really simple, right? It should be pretty easy to do. I should have like a pretty quick thesis. But of course it's not quite that simple. So we have another really big problem, and that's a barrier that's put up by our immune system. So these special cells in our cheeks see little bits of foreign things all the time, like this little bit of a cheeseburger. And in order to prevent our immune system from going crazy at all of these foreign things, they learn to sort of tolerate them. So they're like, oh, I saw this one thing, I don't think I need to react to this. And so we call this idea tolerance. It's a really big problem if we're trying to deliver a vaccine here, though, because when we try to deliver our vaccine, these immune cells are going to tend to just tolerate our vaccine as well, and we're not going to get any of those immune responses that we want. So this is kind of a tricky problem to solve and kind of a complex issue to think about. So let's think about it in a different way. Let's think about if someone is poking you in the arm. So if someone pokes you in the arm once or twice, it's pretty easy to just ignore them. But if someone pokes you constantly for a really long period of time, it's really annoying, and eventually you're gonna react to them. And so we can translate this idea to these special immune cells. So the idea is that if we deliver our vaccine just at one time, we're probably just gonna get a tolerant response. But maybe if we deliver our vaccine constantly over a longer period of time, we can force these cells to respond to our vaccine. And so this is what we're trying to do with this microneedle device is the backing will dissolve really quickly so that you won't just have this thing in your mouth. The needle tips will implant into the tissue and then dissolve really slowly over time to deliver our vaccine constantly to these cells and cause them to become activated. So our system's getting a lot more complex, and I've outlined all of these problems that we're trying to address with it. Let me show you now all of the problems that this device is giving me and what I'm working on. So the first big problem and question that we need to solve is what material can we make this backing out of? It needs to be strong, it needs to be flexible to conform to the cheek tissue, and we want it to dissolve really quickly. The second question is what material do we make these needles out of? We also want them to dissolve but slowly. They also need to be really strong to implant into the tissue. A third question is how do we load our vaccine in there? And how do we control its release to these cells? And then finally, what release kinetics do we need actually cause the activation of these cells. I'm working really hard to answer all of these questions in grad school so that we can make this image of getting a shot in the doctor's office truly a thing of the past. Thank you. Any questions?
So when you were talking about the different delivery methods with the two rubbers, you said you wanted the saliva and then get the antibodies in it. But then with the microneedle patch image, you said you had to get rid of the saliva there.
Right, so we want to get rid of the saliva just for delivering the vaccine, and then what will happen if we can get our vaccine to those special immune cells in the cheek, those cells will cause like this whole immune response within the body that will then generate those antibodies that will be secreted into the mucus later. Does that make sense?
Would the immune response create inflammation in the cheek?
Likely, yes. So we're kind of playing a balancing game with the system of we want a little bit of inflammation to activate those cells, but obviously we want it to not be super painful and uncomfortable for the patient.
How are you planning to have the needles be dissolvable? Are you expecting the cells to digest them, or them to just fall apart in the saliva?
We're using material like polymers that are enzymatically degradable, so that's how they can degrade really slowly.
So besides vaccines, which are like pieces of protein, could this same platform be used for drugs as well, or?
Yeah, so the way we're designing the needles, we can load small molecules, we can load proteins, we can load DNA, so it's theoretically a really generalizable system for any delivery.
Cool.
Yeah.
I have a question.
So
Oh, but you go ahead first.
you're focusing on mucosal membranes, but could the same concept of microneedles be used on like normal skin?
Yeah, so there's a lot of work coming out of Georgia Tech, if anyone wants to do some Googling. They are in the midst of a clinical trial of their microneedle flu vaccine, which is transdermal.
Yeah, so, might sound a little silly, but so with the antibodies in the mucosal membrane, do they just keep getting generated there? Because all I'm thinking of is I'm like, well, that's going to go away in about a minute, but my guess is like it just keeps making them right there.
Yeah.
Do you know why, like, it doesn't just do that anyway? I mean, again, I don't know about biology, but I'm like,
Yeah.
why do you make it on the inside and then not like right there?
Yeah, so the antibodies that are secreted into that mucus layer are really specific for that certain germ that we designed the vaccine for. So without delivering that vaccine that introduces the body to that germ, it wouldn't know to develop those specific antibodies to attack that specific germ.
So I just think I mean, I believe you, obviously. It's just interesting that, like, I'm like, well, mucosal membrane, why won't you do what the rest of the body's doing? It's
Yeah,
like,
yeah, why are they here and not here?
Okay,
Yeah.
cool.
So this idea of the immune cell tolerance to the vaccine, is that also a challenge for traditional needle-driven vaccines?
So the issue of tolerance is mostly just a mucosal membrane issue. Intramuscular delivered vaccines go like straight into the bloodstream, and we, hopefully don't always have foreign objects going into our bloodstream. So the immune cells that live there, like if something foreign's in your blood, they're like on it right away. So I think it's not so much of an issue there.
And how close are you to clinical trials?
Very far.
Several years?
Yeah. Oh, like 20 years probably. But for my actual work, so this is a really cool system, and I do hope that one already within the scope of my thesis. We're hoping that we can use this system to learn a lot more about the immune responses in the mouth. Because yeah, there's a surprising amount that we like don't know still.
That you're talking about how far in the future that is, but is there consideration for how much something like this might cost in comparison to a standard vaccine?
Yeah, definitely. So cost is an interesting issue because there's potentially a lot of cost to develop something like this in a commercial setting. But the other side of that is that a big problem with vaccines right now is that they typically need to be refrigerated. And so I mentioned like part of the goal of eliminating the needle part of the vaccine is that we can get them to rural or developing areas better. And so the possibility that a system like this could eliminate that need for refrigeration could significantly reduce the cost. So there's sort of, yeah, I'm sure like an economist could do like the cost analysis of whether it would actually be worth commercializing something like this.
Yeah, so you're talking about shipping it over, shipping it to foreign countries and all that. Is there, how much has been done about stability? Like, are these things going to stay, molecules going to stay there, they're not going to break down or dissolve or?
Yeah, so I haven't done stability studies on these particular devices yet, but some of the materials technology that's going into the devices, my lab has stability data on, and it's very stable. It stabilizes, we know that it stabilizes proteins really well.